Good morning. So, in today's lecture, would be handling induction type instrument. So, in an induction type instrument, as the name suggests, it works on the principle of induction. That is, when you have a flux produced in a current carrying coil, and this will produce uh, EMF in any magnetic or not magnetic, any electrically conductive material that is placed near this, and magnetic induction results. The limitation of the induction type instrument is that it can be used only for AC measurement, because you need an alternating. You basically need you will basically be able to produce an EMF that is proportional to the rate of change of the uh, flux in the magnetic field. And since you need a rate of change, you need a time varying flux, and hence a time varying voltage or current that is producing this flux. So the variable to be measured, the measurement variable should be time varying, and hence the induction type instrument can also only be used for AC measurement, and it's not useful for DC measurements. On the other hand, the induction type instrument has a good torque to weight ratio, and this is basically because uh, in a manner that is totally opposite to the electrodynamometer type instrument. In an induction type instrument, all the components which carry current are fixed, and the moving component, the moving part, okay, the moving assembly does not carry any current. So the moving assembly can be made light, it need not carry any current, and the fixed assembly, which does carry all the current, can have can be constructed in a manner that significant a magnetic uh, flux of a significant strength can be induced in it. Okay, and it can also, by proper shielding, it can also be made robust against stray magnetic fields. In any way, the magnetic field that is generated in the instrument itself can be made significantly strong, and hence there is inherent robustness against stray magnetic fields. Okay, let's go into the principle of operation of an induction type instrument. So generally, in this instrument, you have one or more poles carrying the carrying a flux that is proportional to the measured quantity. So I have this flux here. If you are measuring a current, the current is the flux is proportional to the current that is powering this flux, and if it's a voltage, that's the measured quantity, then the current that is powering the flux is again proportional to the voltage divided by the impedance of the circuit that is in series with the coil. Okay, in any case, you have, as in this case, you have two poles, and there is magnetic flux that is generating the pole, and these two poles are fixed, and you have a moving disk, and the motion of the disk is going to and because of the flux, there would be eddy currents in this disk due to the induction effect, and the interaction of the eddy currents and this pole and the magnetic flux in this pole is going to cause some torques. So let's look into that in a more detailed manner. Okay, so there are two poles, and they produce two AC fluxes, and in this particular example, both these magnetic fluxes are in a manner that they are going into the paper or into the screen here. Okay, so this is the front view of the assembly and this is the top view of the assembly. And now these are going to cause an eddy current. Okay, and when the flux phi1 interacts with the current I2 and similarly phi2 interacts with I1, you would be able to there would be torque produced as it was in the case of the other instrument that we had seen earlier. Okay, and the effective torque that is acting on this disc would be the summation of these two torques. So in this case we would notice that the torques act in opposite direction, so the effective torque will be tau d1 minus tau d2. Okay, now let us say let's get into the actually quantizing what the torque is. Okay, let's say that the flux phi and the eddy current I are separated by an angle alpha. Now this would mean that the torque that is produced will be the instantaneous torque that is produced will be proportional to phi into I, and or it is phi m im into sine omega t minus phi minus alpha, sorry, not minus phi. Okay, and so over one cycle the mean torque would be very similar to the expression of power, that is, it is phi times I times cos alpha, where alpha is the angle between the flux phi and the current I. And here we have phi and I being the RMS value of these of the flux and the current respectively. Okay, now the expression in the previous slide was dealing with one interaction between one flux and one current. However, we have seen that in the induction instrument we have two fluxes. Let us say they are phi1 and phi2. Let us say there is a phase difference of beta between these two fluxes. So here you have phi1 and here you have phi2, and there is a phase difference of beta between them. Okay, now this phi1, each of them would produce an EMF which lags it by 90 degrees and whose magnitude would be d phi by dt, will be proportional to d phi by dt, which is actually d phi by dt. So E1, if we just go for from phi1, E1 would be minus f times phi m1 into cos omega t. Okay, so you have E1 lagging phi1 by an angle of 90 degrees. Okay, similarly E2 lags phi2 by an angle of 90 degrees here. Okay, now if you see that if you consider capital E1 to be the RMS value of this EMF E1 and I1 is the eddy current that flows in the path caused due to E1, and if the path has an impedance Z angle alpha, then you can say that I1 would have a magnitude E1 by mod Z1, or if you compare it, if you relate it with phi1, you would have F by Z phi1. And again, you would have I1, the eddy current I1 will lag E1 by an angle of alpha because of the assumption of on the impedance value. So in effect, you see that phi1 phi1 leads I1 or I1 lags phi1 by an angle of 90 plus alpha. Okay, and there is a phase difference of say beta between phi1 and phi2, and there is again a similar 90 plus alpha difference between phi2 and I2. Okay, now what we need is the interaction between phi1 and I2, and similarly phi2 and I1. Okay, let's look at that in the next slide. Okay, now from the phasor diagram we have seen that the angle between phi1 and I2, this is 90 degrees plus alpha plus beta, and between phi2 and I1, this will be 90, okay, plus beta minus alpha, minus beta plus alpha. Okay, because how is that coming up? That is, okay, because between phi2 and I2 there is 90 plus alpha, but again between I2 and I1 there is a minus beta difference, because I1 leads I2 by an angle of beta, and because phi1 leads phi2 by an angle of beta, similarly I1 leads I2 by an angle of beta here. Okay, so this effectively means that the torque tau d1, which is an interaction of phi2 and I1, that will be proportional to the product of phi1 and phi2, the frequency f, and this angle cos of 90 minus beta plus alpha. Similarly, tau d2 will be proportional to phi1 phi2 f into cos of 90 plus alpha plus beta. Okay, now what we have here are the magnitudes of tau d1 and tau d2, and we know that the total effect, the total torque, is the summation. Effective torque is the summation of these two torques. But what is the summation of these two torques? Are these two torques acting in the same direction, or they are acting in different directions, in opposite directions? That is also needed to be determined. Okay, now the direction of the torques can be determined by the direction of the currents. Okay, now if the flux is in the direction taken as in the figure, that is going into the screen here, okay, the induced current can be, the direction of the induced current can be determined by the Lenz's law to be these directions as drawn here. Okay, and from that we can say that, let us say there is, let's consider a point here. Okay, now and a point here, one here, and let's say one here. Okay, now you see that the magnetic field phi1 is going into the paper here, and I2, okay, is in this direction, approximately in the vertical direction, pointing down. So this would mean that the torque is going in this direction. Similarly, on the other side, when you go for tau d1, you would see that the torque goes in the opposite direction. Okay, so effectively what you have is that these two torques are acting in opposition, they are not acting in the same direction, they are not acting in unison. So this effectively means that the effective of tau d is tau d1 minus tau d2, or you can also take it as tau d2 minus tau d1, it doesn't matter, but what matters is they act in opposite directions. Okay, and which then means that this effective tau d is proportional to the difference, and this difference can be simplified to this value. Okay, sine beta minus alpha into sine beta plus alpha will turn out to be sine beta cos alpha, twice sine beta cos alpha, but since we are dealing with proportionality, we can just leave it at it. So what we have here is that the total torque tau d is proportional to the product of the two fluxes, the frequency f, and sine of beta and cos of alpha. Okay, now from this you can see that the effective torque is proportional to cos alpha. Now, and to increase the sensitivity, we would need cos alpha to be almost equal to 1. So alpha should be very close to 0. That is, and alpha is the angle between E and I. So which would mean that the eddy current circuit should be a highly resistive circuit. And on the other hand, the torque is also proportional to sine beta. Now beta is the angle between the two fluxes phi1 and phi2. Okay, so in order to again increase the sensitivity, these two fluxes should be in quadrature. Okay, and to achieve this, at least the quadrature part of it, we have certain type of constructions that can be done. One is the Ferraris wheel, Ferraris type induction instrument, wherein you, let us say, if you want to measure a current or the voltage, the circuit is divided into two components. One will be a highly resistive circuit, and one will be an highly inductive circuit using a choke coil. Okay, so you have a coil here, you have a highly inductive coil here, so there will be phi1 generated here, there will be phi2 generated in these two coils. Okay, so you have a non-resistive circuit, non-inductive resistance here going through two of the poles, and you have a highly inductive impedance going through the other two poles. Okay, and you have this aluminum drum which sort of is moving and acting like the what do you call, the moving assembly, and you have a pointer here. Okay, so I said that there are two coils, they are connecting, one is connected with a choke coil and other one is connected with a high value non-inductive resistance respectively, and this would result in two fields, one being the resistive field, one being an inductive field, and whose angle beta is very close to 90 degrees. Okay, and the field that is produced in the resistive part will be in phase with the current that is flowing through the resistive path. Okay, and similarly the field in the inductive path will be in phase with the inductive current. However, the inductive path current will lag the resistive path current by this beta. Okay, and this instrument would operate very similar to the way an induction motor would operate. Okay, and if this is going to be used as an indicating instrument, then the control torque will be generated by using a spring. Okay, that we could see in the this thing. So there is a spring here. Okay, and the damping torque can be generated by the movement of the aluminum of the disc itself in the field of a permanent magnet. Okay, so when this disc is moving, so when you and if you have another permanent magnet here, then the movement of this disc is going to cause any damping that is required. Okay, other type of construction similar to the Ferraris type instrument is a shaded pole induction type instrument. Okay, in this case you don't split the circuit into two parts. Rather, there is no electrical separation. Magnetically you generate two components from the flux with, and you generate a phase difference between these two components, phi u and phi s, and this is generated by having a shaded pole. So what is being done is that the pole of the electromagnet is split into two parts, and one part is shaded using a closed band of a conductor. So maybe you have the pole here, and around this pole you have a band constructed out of copper, and when the flux lines passing through this part would cause eddy currents, and this eddy currents would again generate another magnetic field that will cause a lag in this shaded component. Okay, and of course, and there is a phase shift between these two, between the unshaded and the shaded component, and this phase difference can be caused and can be increased to up to 40 to 50 degrees. And of course, the effect is much less pronounced than that we see in the Ferraris type instrument. However, you don't need to the construction is a little simpler because you just have one coil. Okay, and similar to the case of the Ferraris type instrument, here too the control torque is provided by a spring, and the damping can be generated by the motion of this disc in the field of a permanent magnet. Okay, now let us look at the usage of the induction type instrument as a voltmeter or ammeter. Now in both of the cases, both the fluxes, the unshaded or the shaded, or the resistive or the inductive case, the fluxes, both of them will be proportional to the current or the voltage that is being measured. Okay, and so the total torque will be proportional to the square of the current or the square of the voltage. In effect, the scale here is going to be non-linear when you use an induction type instrument as a ammeter or voltmeter. Let's look into the advantage and disadvantage of the induction type instrument. Because the moving component can be made very light and not current carrying, usually you have a very light aluminum disc, as a moving component, and you can have uh, jewel bearings to support the aluminum disc. And so what you end up with is a very low friction uh, instrument. And in addition, since the current carrying components are not going to be moving components at all, it can have a high torque to weight ratio. Okay, and since strong magnetic fields can be generated in the instrument, uh, the effect of stray magnetic fields is not so significant, so it is robust against stray magnetic fields. And since you can have magnetic damping, and you need and due to the robustness in the magnetic field against state magnetic fields, you can use a permanent magnet for the damping purpose, as opposed to reliance on air friction damping or something of that sort. And so good damping can also be achieved in case of an induction type instrument. Okay, coming to the disadvantage, uh, due to the fact that you are powering the coils, it may lead to higher power consumption by the instrument itself. Of course, because to generate this high torque to weight ratio, okay, you would need significant power consumption by the instrument also. Okay, generally, due to the construction, the induction type instrument is costlier than a PMMC or a moving coil instrument. Okay, one thing that is to be noted is that the reading was always dependent on what frequency, for the frequency of operation. So it was, you see that the flux was phi 1 phi 2 f and cos alpha sin beta. Okay, so this f component, the frequency sensitivity, is already always there. It cannot be used for DC, it can only be used for AC. That is another disadvantage. And if you are going to use it for voltage as a voltmeter or an ammeter, you would end up with a non-uniform scale. Okay, so because of the significant restrictions in the measurement, the induction type instrument is not really the instrument of choice when you want voltage or current measurement. It is usually used for other type of measurements, okay, where different quantities, so phi 1 and phi 2, are not generated or not caused by the same quantity, they are caused by different quantities. So probably something like power or energy measurement, that are more suited applications for the induction type instrument. So going further, so this is the chapter 8 in A.K. Sawhney's book. Okay, can be referred to for further reading. Okay, so in the next class, we would look further into the usage of induction type instrument in power and energy measurement. Okay, so with that, we come to the end of this lecture. Thank you for your patience.